This is theory for analysis of covariance in CRD. Just see what is the analysis of covariance that we will see first, and then we'll see its practical. Analysis of covariance with one concomitant variable. Analysis of variance is a technique of increasing the precision of design by reducing the experimental error. ANOVA is a technique in which it is possible to control certain sources of variations by taking an additional observation on each of the experimental units. Let us suppose that in an experiment y is the response variable, means the variable which we are interested, and x is the another variable. X is called as here covariate, or it is called as concomitant variable, or it is independent variable, or it is also called as ancillary variable. Different names are given to that variable x here. In ANOVA, we adjust for the variation in response variable y, linear regression of independent variable x here. If it is not done, then the error mean square will be inflated due to the linear effect of x, thus making it difficult to detect the true differences in the response variable. ANOVA procedure is a combination of analysis of variance and regression analysis. This we have seen, ANOVA we know, and regression analysis also you are knowing. So combination of these two is nothing but ANOVA here, where we are using analysis of covariance. That we see examples here. See first example, suppose we want to compare the effect of some drugs on reduction in weight of persons. In this case, we take y as response variable. Mean weight of taking means weight of taking drugs after a specified period. What is our variable y here? Response variable means after some duration we are measuring the weights of the person. That is our response variable. That is we are interested here. During some specified period here, suppose number of days, or after number of weeks or months, we'll note down the weight of the person after taking the drugs here. And x as the initial weight of persons at the time of starting the experiment is a concomitant variable, means here x is also important here. What is that x here? We are calling here initial weight of persons at the time of starting the experiment. That is also important here. Okay, so this we are having as the concomitant variable, or it is the ancillary variable in this case. Second example we are having, suppose we want to compare different methods of teaching, classroom teaching, online teaching, correspondence, etc. Different methods are there. So if we are comparing these methods of teaching by observing the scores of the students, all of whom take the same final exam, the variation in the scores of students may be due to only the different methods of teaching, but also depends on the IQ levels of the students. So here this IQ level is also important, not the different methods here. Here x we are calling as the IQ levels of the students here, and that is also there. Okay, so such a way we are having as the ancillary variable or covariate we are studying here. So how we'll do this analysis? Analysis of covariance for one-way classification with single concomitant variable in CRD. Let us suppose that we are comparing V treatments. We call those treatments as T1, T2 dash 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 TV. Ith treatment replicated Ri times, like in our CRD. In CRD we have considered Ni times, that ith treatment gets replicated. Here we have taken as Ri here. Ri times each treatment replicated. So that n is equal to small n is equal to summation of Ri is the total number of experimental units here, V treatments we are having. So because of that we are having this summation of Ri I from 1 to V here. If we add all those replications there, so we'll get total number of observations here for that experiment, corresponding experiment. Suppose that along with the response variable y, this is the response variable we are having related to this treatments here. We are applying those treatments. We consider a single concomitant variable x here. Here we are considering a single variable as x here, concomitant variable. Then assuming a linear relationship between the response variable y and concomitant variable x, some relationship they are having. The linear ANOVA model consists of the sum of two components. How we are getting that ANOVA? That is, first component is there, that is the same component as in ANOVA, and second component, the component due to the regression of y on x. This we are getting as the additional here, y on x, that is the component related to the regression of y on x. The statistical model for ANOVA for CRD with one concomitant variable is given by Yij equal to mu plus alpha I plus beta into Xij minus x bar dot dot plus epsilon ij. I takes value 1 to V, j from 1 to Ri here, where this mu denotes the general mean effect. Like in ANOVA we are having this mu as the general mean effect. Alpha I is the effect, fixed effect due to I treatment, that also we are having in ANOVA. I takes value here 1 to V treatments we are having. Epsilon ij is the random error effect, that also we are having in ANOVA. Only this newly introduced here, beta is the regression coefficient of y on x, and xij is the value of the concomitant variable corresponding to the response variable yij. Means for every yij we are having the corresponding xij value that we are having here. Okay. And what we are doing here, we are making these two assumptions here, summation of I from 1 to V alpha equal to 0 and epsilon ij's are IID normal 0 sigma square, and by using these assumptions we are estimating the different sums we are finding here.